because for this I need to compute E, G and F, and hence I need to compute the normals actually, which are going in the ambient dimension, in the third dimension. But we're going to see that this quantity, is the quantity which is intrinsic to the surface actually. In other words, you can know the surface entirely from the Gaussian curvature, and you don't need any reference to the ambient dimension. And that's what makes it remarkable. That I can sit on the manifold, I can sit on a sphere. Okay, so in other words, if I have a bug, okay, so in curves I know, so there is what you call the fundamental theorem of curves. In curve theory, we proved actually a result which says that if you have any two regular good curves, which are parameterized by arc length, they are locally indistinguishable. You can't distinguish them actually. So in other words, if two small bugs are living on two different curves which are parameterized by arc length, they can't distinguish themselves actually. That okay, are they living on the same curve or different curves actually. But in two dimension, if a bug is sitting on a sphere, okay, then and if the bug is a little bit more sophisticated and is able to compute the Gaussian curvature of that surface, then he's going to know that what kind of surface he's living at. Because think about it, sphere, so the plane and slender and the cone has a Gaussian curvature 0, while the sphere has a Gaussian curvature, we can prove it positive actually. So there must be some fundamental difference between sphere and a plane, sphere and a cone actually, sphere and a slender actually. Okay? And this fundamental difference, you can explore it through the Gaussian curvature. Okay? So in other words, if you compute Gaussian curvature and it turns out that it is something positive at a point, it's something positive or negative or 0, it tells you, it gives you a good information about the neighborhood of a small surface actually, at that point. Okay? So the Gaussian curvature is an important quantity. Okay? So in other words, that's what the question that Gauss asked actually, that how fundamentally a sphere is different from a plane, maybe a cylinder, or how a torus is different from a sphere fundamentally. Okay? And the difference that he pointed out is that all these species have their own Gaussian curvature. It's the Gaussian curvature that makes them different actually. You can compute it and you can know that, okay, that's the Gaussian curvature, okay, that basically, the bug will be able to tell the difference actually, okay, that I'm sitting on a torus or I'm sitting on a sphere actually, by computing the Gaussian curvature, okay. So the Gaussian curvature is the intrinsic property of the surface. We don't need the ambient reference to the ambient dimension. At the moment we can't see it, because at the moment we need first and second fundamental form. Okay? But you will see that in order to compute the Gaussian curvature, I don't need second fundamental form. I can purely compute it from the first fundamental form. So if there is no second fundamental form, so there is no reference to the normal vector. And whatever is happening on, so on the surface, like if you compute it through first fundamental form, then this is, that property is going to be the intrinsic property. Is it making sense? That's what we are heading. Okay, maybe that we're going to end the course. We have some more minutes. How many minutes do we have? 20 minutes. So see, it's just something Gaussian, it's nothing too fancy. So that is the classical formulation. In other words, if you want to compute the principal curvature, you solve this quadratic equation. Okay, or you can do this, that if you compute these first and second fundamental form coefficient and just substitute them here and treat K1 and K2 as unknown and solve this system of equation for K1 and K2, and you're going to get the principal curvature. So that's what we call it.